Today we're going to be talking about acceleration and kinematic formulas. So first of all, what is it that defines acceleration? Remember that acceleration is the rate of change in velocity. So what is velocity? Remember, velocity is speed and direction put together. So take a situation like this. We have a quarter-mile race occurring.
Oh, train almost lost. Fucking pet almost lost tractor. Okay.
Right? As the race went on, the cars went faster. We also have a relationship between position and velocity. As velocity increased, the cars covered more position in a set period of time. But we also had a relationship between acceleration and the displacement. The car that accelerated faster moved a farther distance in the same period of time. So to relate all of these, we have a couple kinematic formulas. And we're going to run through those real quick and give a couple examples of how we can use each of them. So first, let's go back to the ones that we've used previously. We have defined velocity as the change in position divided by the change in time. Now notice this equation only has velocity, displacement, and the time differential in it. So we could not use this equation if acceleration is present. This only works when acceleration is not present, when we have constant velocity. Let's rearrange this equation real quick to simplify, or at least to look at it in a different way. We're going to multiply both sides by delta t. And thus we have delta x equals velocity times the time differential. So delta x equals vt is our first kinematics formula, and we have used that previously. An example of how we might use this: if a vehicle is going at 60 miles an hour for 3 hours, how far has it moved? So a vehicle is moving at 60 miles per hour for 3 hours, and we're trying to find delta x. Let's identify our givens. 60 miles per hour is the velocity, and 3 hours is the time. Let's write our equation. Delta x equals vt. Delta x equals the velocity, which is 60, times the time, which is 3. We don't need to use the delta time here because we were just given one straight time. And so delta x equals 6 times 3 is 18. Add the 0, 180 miles. Okay? We've already used that equation several times. We did a whole worksheet on it. And so now let's move on to a second equation. Here, this is our quarter mile equation, like the video we saw. This is what relates displacement with acceleration. So delta x equals the initial velocity times time plus 1/2 times the acceleration times time squared. If you've taken calculus, or if you've taken calculus B at this point, you will recognize that this equation is the integral of this equation. And there's several other proofs we can do to get the equation, but for now, it's more important that you see it and you recognize the important parts of it. First, there is a squared relationship between distance and time. If we were to double the distance on the quarter mile to instead a half-mile race, and everything else stayed the same, we would expect the cars to take not twice as long, but instead root 2 times as long. because the cars are already moving, they would already be up to a higher speed. It's not like it would take them twice as long to cover the distance, and that's because of that square in that formula. Some other things you may notice. This part of the formula is the same as this formula. This part of the formula is just saying the initial velocity times time is going to give us a certain amount of displacement. And this part of the formula is the effect of acceleration on that displacement. Let's do a practice problem just to find out how we can apply this. Suppose we have a skateboarder. This skateboarder is going to start from rest, and he's going to accelerate at a rate of 3 meters per second for 5 seconds. What I want to know is how far has this skateboarder moved in that time? So let's write our equation. Delta x equals VIT plus 1 half AT squared. Remember, from rest means our initial velocity is 0. 0 times anything is 0. So in this case, because I have an initial velocity of 0, I can cross out that first expression. So delta x equals 1 half AT squared. Delta x equals 1 half. The acceleration is 3. The time is 5 squared. Delta x equals 1 half times 3 times 25. I picked fun numbers. So 25 times 3, of course, is 75. Divided by 2 is 37.5. X equals 37.5 meters. What is this shown? This skateboarder, starting from rest, sped up at a certain rate for a certain amount of time, and in that amount of time, accelerating at that rate, he was able to move that distance. Let's solve for something else. So, how long is a quarter mile in meters? And let's see. Give me just a second. I'll look that up. So 0.25 miles is about 400 meters. So let's say we are in a quarter mile race. I wouldn't recommend it. It's dangerous and expensive. But 400 meters is the distance that we plan to move. And let's say that our car, we go to this race, and with your, stock Corolla, you go into this race and you hit the gas and you finish this quarter mile race in 4 seconds. And of course, you're starting from rest because that wouldn't be a very fair race if you got a head start on everybody else. And what we want to find out is if you go 400 meters in 4 seconds and you're starting from rest, we want to know what was the Corolla's rate of acceleration. So let's use our equation. How do we know to use this equation? Because we have delta x here and we're looking for acceleration. This is the only formula that relates delta x and acceleration that we've used so far. There's one more that we'll look at in a little bit. So delta x equals VIT plus 1 half AT squared. Delta x is 400. VI is 0, which means that'll all go away because anything times 0 is 0. 1 half A, and then the time 4 squared. We'll do our order of operations. Exponents comes first. 4 times 4 is 16. 16 divided by 2 is 8. Now 400 divided by 8, which should be pretty straightforward because 8 times 5 is 40, right? So that would be 50. Let me make sure that's right. Yes, 50 meters per second per second. That's an incredible rate of acceleration for that Corolla. Maybe you didn't have a stock Corolla after all. Maybe you attach rockets to it. All right, so that is the displacement formula with acceleration. Let's add one more formula in. Suppose now instead we wanted to know how far a car had to move if it were accelerating a set rate in order to speed up from one speed to another. To find this out, we'll need to use this formula. And what this formula comes from is us combining our basic acceleration formula with our basic velocity formula. So let's use this equation. Suppose we are driving at, let's say, 12 meters per second is our initial velocity. And we're going to accelerate at a much more reasonable 4 meters per second. And we want to know how far we have to go in order to speed up to 22 meters per second. That'd be our VF. So once again, we're driving at 12 meters per second, and we hit the gas and accelerate at 4 meters per second squared. How far will we go before we're going 22 meters per second? In other words, will we have enough room to do so before we rear end that truck in front of us? So let's write our equation. V squared equals VI squared plus 2A delta X. Now, a reasonable question here would be, how do I know I need to use this formula and not the delta X equals VIT plus 1/2 AT squared formula? Well, the biggest difference is in that formula, in the 1/2 AT squared formula, you'll notice there was a T squared. Nowhere here do you have a T in this equation. Time is not a part of this equation. And the only equation we have in which time does not play a part at all is this equation. Instead, we have an initial velocity, a final velocity, acceleration, and we're looking for displacement. So let's plug those in. Final velocity is 22 squared equals the initial velocity 12 squared plus 2 times 4 times delta x. Order of operations, we need to do our square first. So 22 squared is 484. And 12 squared is 144 plus 8 delta x. Step 2. We have a variable here, so we need to get this expression alone. Let's get rid of the 144 by subtracting it from both sides. Okay, by subtracting it from this side, we can eliminate 144, and then 484 minus 144, 484 minus 144 gives us 340. And then we just copy the 8 delta x down. Now to get the delta x alone, we need to divide by 8 on both sides. 340 divided by 8 gives us 42.5 meters, since that's what we're working in since the beginning. And so It takes us 42.5 meters to speed up from 12 meters a second to 22 meters per second if we're accelerating at 4 meters per second, or 4 meters per second squared. Let's do one more one more piece of work with this equation. Suppose that we have a slow roller, that spindle, and that spindle accelerates at a rate of, it was about 1 meter per second squared, wasn't it? So let's make it 1.5 meters per second squared. So it'll be slightly different than our earlier calculations. And we want to know, I mean, this thing will eventually get up to like 60 miles an hour, won't it? I mean, 60 miles an hour. And so 60 miles an hour, in fact, let's go like 70 miles an hour. We want it to get up to 30 meters per second. How far would our ramp have to be? How long would our ramp have to be in order for it to reach 30 meters a second, which is like 70 miles an hour? Delta x equals, we don't know. We do know what speed it's going to start at, right? 0, because we just put it down and let it start rolling. So let's write in our equation, v squared equals vi squared plus 2a delta x. You'll notice we have to use this equation because there's no time here. So vf squared, 30 squared, equals vi, which is 0, so we could honestly just leave all that alone, plus 2, 1.5 times delta x. So 30 squared, 900, equals 2 times 1.5, which would be 3 delta x. So 900 divided by 3 is 300 meters. If we had a ramp 300 meters long, tilted at the same angle as our slow roller ramp, we could get this thing up to 70 miles an hour. That'd be amazing, wouldn't it? All right, let's do one more where we solve for a different variable, since both those times I solved for delta x. Let's instead say that we don't have a 300 meter long ramp. Let's say we only have let's say 100 meter long ramp. So now we have our delta x as 100 meters. That's as long as our ramp is. We still know our acceleration is 1.5 meter per second squared, and we know our initial velocity is still 0. How fast could we get it going? How fast, if we had a 100 meter long ramp, would our slow roller end up going if it was accelerating at 1.5 meters per second squared? Again, no time here, so we have to use v squared equals vi squared plus 2a delta x. V squared, that's what we're trying to figure out. Vi squared is 0, once again. 2, the acceleration is 1.5, and the delta x is 100 meters. So v squared equals, all that's gone, 2 times 1.5 is 3 times 100. 3 times 100 is 300, and then the square root of 300 is, I need a calculator for this. I cannot do a square root off the top of my head. 17.3 meters per second. So if our ramp was only 100 meters long, we could not get it up to 70 miles an hour. We could get it up to 17.3 meters per second. And just a quick check in as to how fast that is. So if we were saying 17.3 meters a second, that's almost 40 miles an hour. That's like 39 miles an hour-ish. All right, hopefully this helped seeing examples from the 3 equations. Now I'm going to write the 3 equations down. Delta x equals vt delta x equals v I t plus 1/2 at squared. I'm actually going to make this average. And then v squared equals vi squared plus 2a delta x. There's one more. V equals vi plus at. Where did this come from? Acceleration is change in velocity over change in time. Multiply both sides by time, and we get that delta v equals a delta t. Now let's break that delta apart into vf minus vi, because that's what delta is, equals a delta t. And let's add that vi to the other side. Vf equals vi plus at. That's where that formula came from. We've already been using that. When we did the acceleration worksheet, the acceleration formula worksheet, we use this all over the place. This is just a rearrangement of it. Now we have 4 equations. How do we know which one to use in each circumstance? The answer is based on our givens. This one is only, let me say it one more time, only used when there is no acceleration. This one is used when we are comparing displacement, acceleration, and time. Our givens, or what we're asked for, have to include displacement, acceleration, and time. This one cannot include time. This one must have an initial velocity and a final velocity and acceleration and displacement. And this one is what relates initial, final velocity with time. So notice these two both have displacement in them. What determines which one we use is whether we have time or whether we have final velocity. These two both have final velocity in them. What determines what we use is whether we have time or whether we have displacement. That's it for these notes. Please ask in the live session if you have any questions.